So the third item that we talk about in terms of verification is the testing. So in testing, you really try to make sure to show that the software is actually performing what it's supposed to do, and of course that the software is kind of free of errors. So that's what you try to achieve, show, prove, demonstrate by performing software testing activities. Well, if you look at D178C, it kind of establishes three software testing activities. First one is low-level testing. In this case, you try to verify that all the low-level requirements have been implemented correctly. The second item is the software integration testing. You try to verify that the interrelationship between the various software components and requirements are okay, and that the software requirements and especially the architecture is implemented correctly. Remember, in the architecture we try to establish all kind of these requirements, all the modules and how they interact. And then of course finally we do the hardware-software integration testing, in which case we try to establish if the software is operating correctly on the target computer and in the target environment. Now, one thing to know about all the testing that you do in D178C is all the test cases should be based on the software requirement, not on the source code. Yeah? So based on the low-level requirements or even high-level requirements, you're going to derive a set of software test cases. This is different from testing in which you look at the source code and derive your test cases, which we refer to typically as structural testing. Yeah? So in structural testing, you derive your test scenarios, your test cases from the source code, not the requirements. In D178B and C, they say you really need to derive your test cases from the software requirements. Well, another way to look at that in software engineering is that if you base your test cases on the code, we refer to that as white box testing. Whereas if we treat the code as a black box and only going to look at the requirements, then we call that black box testing. So the problem with white box testing is that if there's already an error in your source code and you use the source code to derive your test cases, you're not going to fix that problem. Whereas if you derive it from your requirements, at least you know that if there is when a test case actually results in an inconsistent outcome, in other words, an indication, the expected outcome of the test is not what you see when you actually perform the test, then is more an indication that, okay, the source code implementation is not reflecting what was specified in the requirements. Again, this is another, I put two definitions down here that from a reference given below, just for extra information. Of course, there's a variety of these items, and you can go in the literature to find both on the white box testing and the black box testing a variety of different things that people have used. Well, we're going to talk about some of those in the next couple of slides. I guess the slide's the same. Okay, now another way, and I got this from the NASA Software Guidance Safety Guidebook, and also from a presentation by Cantata, or IPL, that makes Cantata, that looks at, often what you see people talking about, okay, we talk about unit testing versus integration testing. Of course, in this case, unit testing would be tests performed on a software unit. Think about it as a module or a class or not a component. And one thing you could say is I can see that could be possibly like maybe one file that contains one subroutine or a function. And in C++, that could be maybe one class. Yeah? Now what you then can do, you can take that unit and put it inside a test harness and perform all the tests that are required. In the integration testing, what you're trying to do is you actually perform the test on a group of software units together. Yeah? In this case, you want to try to figure out how these individual units interact. So you're looking at inter-process communication, and or the interface between the functions and external hardware and software. Think about memory allocation and deallocation between the units, and call sequences. Okay, so one thing that I got this from IPL. So you look at, okay, you design your architecture and detailed design. So these are your, and then your units. And then of course you can actually make a unit, in other words a file with a function in it, and test it. Then you actually take a couple units and put them together. And you perform the integrated test. And then when you're all done, you can also perform the whole system test, acceptance test. So this is, of course, one way of looking at it. In addition to DO178C, but it more or less address the hierarchical way of performing tests. Now, the slide 35 and 36 are two different ways you can set up the tests. First one is stubbing, in which case if you take a software unit or software module and rather than interfacing it with the external software, for example, the main from which you call this subroutine, or rather than actually having to talk to an external hardware component, you kind of stub that external software or hardware by some external program. In other words, you kind of make a test harness and make it look to the module as if it's talking to some external device or software component. In wrapping, it's really you're just going to have the external object and you just put an intermediate set of software or hardware in between that kind of acts as an operator between what comes out of your module source code going to the external object and what comes back. And this allows you to take certain things that you normally get as a response from the external object and replace it by other inputs or outputs. Now, for software testing, of course, it's very important to describe, in terms of lifecycle data, what the test cases are and how to perform these tests. We call those test procedures. How are we going to do these tests? Are we going to, take if I have a particular set of low-level requirements that are representing a module, am I going to take this module, write a test harness around it, then put it on a piece of hardware? These are all part of the test procedures. And of course, when you execute the test, you need to document it. An important thing to find out there is like, what is the expected outcome of the test versus what is the measured outcome. And of course, traceability. The test must be traced back to the requirements. Now, if you look at the test cases, we typically break it down into performing what we call normal range test cases, in which case we're going to just exercise the real integer value variables. We exercise the time dependencies, the state transitions, the logic equations within their normal ranges. Within the ranges that they're supposed to be in. And I'll talk about that real quickly. And we're going to perform some robustness range test cases. Actually, we're going to check out if there are some abnormal values of some of these integers or reals or time dependencies that we want to check out. Okay. These things include arithmetic over and underflow, state transitions that not really are allowed or shouldn't exist, an abnormal system initialization that you wouldn't expect, but let's check it out anyways, to check out if the code is robust against these. Now, one thing that you see in this slide, it talks about equivalence classes. And by equivalence classes, we really mean a partition of the input domain of a program such that a test of a representative value of the class is equivalent to the test of other values of the class. Now, suppose we have this equation here. We have y equals 1 plus kx plus 0.3 kx squared. And then suppose that's given that k must be between 2 and 0 and x must be between 0 and 255. So this is the input domain of that equation. Well, since this is a continuous equation, that means that I could pick any value of k between 0 and 2, and any value between x between 0 and 255 will be representative for this equation, hence because it's continuous. So k is 1 is just as representative as k is 1.4. The output value is going to be different, but they're still just as representative. So we can use k as 1 as equivalent for this particular domain. Well, in this case, you can also identify the robustness tests, which are testing at the boundaries. I could pick k equals to 0, or just a little bit bigger than 0, or 2, or just a little smaller than 2. It could be also exactly at 0, or just a little smaller than 0. Yeah. In these cases, this equation should be, if you pick a k that's smaller than 0, this one should not exist. So the program should not return you with this value of y because it's outside the range. So for you to test that, you also have to make sure that I'm testing these kind of values for k and x that fall outside the normal input domain. So in one way, you can actually get the valid data that you need to put in, the normal range, and invalid data that is actually that you need to kind of test in your robustness test cases. So data outside the bounds of the program, or that's physically even impossible. Yeah. And then of course, state transition diagrams could mean I'm looking at state transitions that would never be possible. Yeah. So typically 0 to 1 exists, but for example, 0 to 2 does not exist. Now, the next 3 slides give you a nice kind of table of things that you would find, the errors that would be revealed in software testing at a low level, integration testing, and hardware-software integration testing. I'm not going to really go into detail. You can just read this list. But things like incorrect loop operation, incorrect logic decisions, maybe because you make a statement like if x is smaller than 2 rather than if x is smaller or equal than 2. These are the kind of things that you find in low-level testing. In software integration testing, it's really all about the interfaces between the software modules. So you find things like parameter passing errors or data corruption errors. And then of course, finally in hardware software integration testing, you find the errors that are typical from running the software on a particular hardware component that you proposed in your PSAC. So, things like interrupt handling because you picked a wrong interrupt vector. You picked an interrupt vector that was not present, for example, on this particular your target hardware.